Morning, everyone. This is George Chen. I'm the product marketing manager for isolated and high power solutions at MPS. And today we'll have a webinar related to the isolated power solutions for industrial, renewable energy, and EV ecosystems. Here's a quick look at the agenda that we'll cover today. First, we'll take a look at some of the renewable energy applications, including solar inverters, DC fast charging stations, electric vehicles, energy storage, automation, and drives. We'll take a quick look at some of the system overviews for these blocks. I'll have a discussion on some of the advantages of LLC topologies versus flybacks as the preferred power supply topology for biasing silicon carbide as well as IGBTs. I'll give a quick overview of our isolated gate driver and power modules, and then some of the digital isolators from MPS as well. So if you look at the rise of green energy, decarbonization is driving a massive shift in the renewable energy infrastructure. This covers from the power plant side, starting with the solar inverters, energy storage to make sure that the power can be captured during the day and then used throughout a 24-hour period. DC fast charging stations as part of the electric vehicle infrastructure, electric vehicle, and then automation and drives, which are all becoming higher and higher power. Many of these systems are actually shifting to 400-volt backplanes or 800-volt backplanes, and that's really driving the need for silicon carbide to really maximize the efficiency and power density of the entire system. Typically, if you look historically, the power supplies that have been used for driving silicon carbide or IGBT MOSFETs have typically been flybacks in the past, but more recently, especially to have better resistance to higher DVDTs from silicon carbide, soft switching topologies such as LLCs are being used more and more often. And part of the reason this happens is because with an LLC solution, it can actually have an increased isolation voltage as well as smaller total solution size. Here, this is a projection that we've seen for EV sales volumes. So in 2021, there were about 6.8 million electric vehicles shipped. Last year in 2022, about 10.5 million. The estimates for 2023 have been right around 14 million units of electric vehicles. And we see going into 25 and 26, we're seeing a 2 to 3x increase again, up to over 30 million units by 2026. When you look at the applications, especially for silicon carbide and silicon carbide power supplies, about 70% of that is used in traction inverter applications and 30% being used for onboard chargers, the DC-DC converter for 400 volt to 48 volt or 48 to 12 volt even, BMS and other auxiliary power supplies. As the world strives for carbon neutrality, electric vehicles are rapidly taking market share from internal combustion vehicles. So actually billions of dollars are currently being invested by the top automotive OEMs worldwide in order to really electrify their vehicle lineups with a mixture of both battery electric vehicles as well as plug-in hybrids. So as you saw in the previous chart, in 2021 alone, the number of electric vehicles sold actually doubled compared to the number of vehicles sold in 2020. And then here we're listing some of the typical electric vehicle systems that are needed within an electric vehicle. So battery management systems that help manage battery health, state of charge, and vehicle cell balancing. The onboard chargers used to help convert the AC voltage from the grid into a DC voltage, typically somewhere between 200, 400, or 800 volts using an AC charger. So if you think about the chargers that you might have at your house or at work, that's typically an AC charger that has the energy converted by the onboard charger on the vehicle. And then we've seen that a lot of systems that have the onboard charger are actually integrating the DC-DC converter as well. And so that's typically a 48 to 12 volt or 400 to 48 volt DC-DC converter. And then lastly, we have the traction inverter, which converts the energy from a high voltage battery. So that battery is typically 400 or 800 volts to drive electric motors. And then that also helps with recuperating energy from the regenerative braking. Next we have here, so this is a block diagram for a DC fast charging system. So this block diagram shows the conversion from a 3-phase AC voltage into a 250 or 800 volt DC voltage that's used to charge electric vehicles. A DC fast charging station typically contains several of these subunits. So this block diagram we have here is what I would call a subunit. And each of these subunits is typically between 30 kilowatts up to 75 kilowatts. And the way that DC fast charging stations are able to achieve 250, 350 kilowatts, or even higher amounts of power is that multiple of these subunits are placed in parallel. The DC fast charging system is generally comprised of two conversion stages. The first stage is a power factor correction stage, which converts the AC voltage from the power grid into an intermediate DC bus voltage that's typically between 800 volts to 1300 volts. Typically, a three-phase, three-level rectifier or inverter topology is commonly used for this PFC stage. And then this particular topology refers to a three-level converter that can interface with a three-phase power grid. The next stage is the DC-DC stage, where an isolated DC-DC converts the intermediate DC voltage to the target voltage that's specified to the battery being charged. So basically, when you plug your electric vehicle into a DC fast charging station, there is a handshake that is made between the vehicle and the charging stations that determines whether the car should be charged at 400 volts or 800 volts. LLC and phase shift full bridge converters are pretty common topologies for the DC-DC stage. And then there's several different products from MPS, such as isolated gate drivers, gate driver power supplies, isolated power modules with integrated transformers, as well as integrated inductors, as well as current sensors for DC fast charging stations. Some of the biggest challenges we see in this application are really maximizing power density, reducing cost, and reducing the overall size. So right now, I'll show you a quick look at the entire roadmap from MPS for isolated gate drivers and power supplies. Most of these products are mainly focused on our non-automotive grade products, but we do have some automotive grade products available here as well. So the first products that I'll be diving deep into are the isolated power supplies on the right-hand side of this page. So we'll go over the MPQ 18913. This is a discrete gate driver power supply that can be used to create a plus 20 minus 4 volts, plus 15 minus 4 volts for driving silicon carbide. I also have the MID 1W and MID 3W, which are power module versions of MPQ 18913. And so they have integrated transformers. So if you see the name as MID or MIE, that means it is a power module from MPS. 1W or 3W stands for 1 watt or 3 watts of power. And then the last four digits, 2424 or 0505, is the input as well as the output voltage for these devices, and kind of talks to what the transformer turns ratio is. So 2424 means a 1-to-1 turns ratio. If you provide 24 volts on the input, you will get a differential of 24 volts on the output. So you can get a plus 15 minus 8 or a plus 20 minus 4 volts, for example. So this first product here, this is the MPQ 18913. This is our gate driver power supply for silicon carbide as well as IGBTs. This does take an LLC topology. And so in a few slides, I would dive deeper into LLC topology, some advantages versus flybacks. We do have a configurable frequency from 750 kilohertz up to 5 megahertz for the 18913, and then 10 megahertz for the 18914. This part also comes with automatic resonant frequency detection, as well as an optional spread spectrum for EMI reduction. We have a host of different protection features, such as overcurrent protection, short circuit protection, over voltage protection, over temperature protection, and then there is a fault reporting pin so that if any of these faults triggers, we can let the MCU know that there is an issue with the power supply for the silicon carbide or the IGBTs. The power level for this device is up to about 5 or 6 watts of power, and this is available in a tiny 2 by 2.5 millimeter package with wettable flinks, which does enable optical inspection. The 18913 is a fully qualified automotive product, and you can see in this block diagram here, we do have an LLC, and then we're providing a plus 20 or negative 4 volts, but plus 15 minus 4, plus 15 minus 8 are all really common voltages that we see with this sort of device. And as I mentioned earlier, some of the applications include IGBT or silicon carbide gate driver bias, EV fast charging stations, traction inverters, and onboard chargers as well. One of the big advantages of this MPQ 18913 is that it does have a very high switching frequency, and that allows us to really reduce the size of the transformer. So the evaluation board that we show here actually does have a planar transformers with windings directly on the PCB, and that's to really help reduce the total solution size. And then we also have a second evaluation board available that does have a traditional bobbin transformer. And on the right-hand side here, we do have the efficiency. So this is basically showing a 21.6 to 26.4 input voltage while maintaining an output voltage of 24 volts. And then at 1.33 megahertz switching frequency, at full load, we're achieving about 85% efficiency. And then the peak efficiency at about 150 milliamps is right around 87%. So this is a very high efficiency topology for creating these gate driver power supplies. The next product we have here, this is the MID 1W2424. So this is a module version of the isolated power supply that we were just showing earlier. So the input voltage range for this device is 5 to 30 volts with surges up to 50 volts. We have different versions for either 3 kV or 5 kV RMS isolation, depending on what the requirements of your application are. The output power is 1.5 watts. One of the big things to note is that this is an integrated transformer, so we do have the winding inside this package, but at the same time, it's available in a very standard SOIC 16 wide body package that's only 2.65 millimeters tall. We are able to achieve a COM mode transient immunity of 100 kilovolts per microsecond, and then this device also has a very optimized isolation capacitance of only 8 picofarads for this device. So both these products that I've shown here are typically competing against legacy flybacks. And so here we have a PCB footprint analysis of these isolated bias supplies. So on the left-hand side, we're showing the discrete version of this device, the MPQ 18913. This has a total solution area of about 109 millimeters squared. And then if we look at a competitor flyback, in this case, we're looking at a primary side regulated flyback. You can see that the solution size is actually much larger. And a large portion of this is because of the switching frequency of the LLC, which can go up to 5 megahertz or even 10 megahertz. And typically, when you look at a flyback, the switching frequency is 1 megahertz or less. And for automotive applications, a lot of times it operates at about 400 kilohertz or even 200 kilohertz. And that's what's resulting in a much larger transformer, as well as larger amounts of output capacitance. We can see here that we also took a look at the total number of components. So 21 external components for the 18913 versus 26 for the flyback. And in total, with the LLC, we can achieve a 40% smaller solution size compared to a flyback. So with the smaller solution size, we also see typically a lower total bill of material cost as well. So on the left-hand side, again, I'm showing the 18913 and the LLC resin topology. The high voltage cap, it does have a little bit more compared to a PSR flyback on the right-hand side. You can see there's quite a bit of money saved on the low voltage caps. Again, this comes back to the higher switching frequency. And then we also have quite a bit of cost savings in not needing extra Zener diodes or switching diodes. And then in the transformer itself, we also have a little bit of savings because the transformer is 11 by 6, 13 microhenries versus 30 microhenries in a 9 by 10 millimeter transformer. And ultimately, assume the cost of both these ICs will be very similar. The biggest difference is that the BOM cost, excluding the IC itself, is 59 cents for the LLC and about $1.10 at high volume for these PSR flybacks. So you can see that if you compare only the external BOM cost, we're achieving about 46% lower BOM cost. And then the value of X will actually be very similar, if not slightly cheaper, for the LLC resonant topology. We've also done a comparison of both the products that I showed earlier. So the 18913, the discrete solution, versus the MID 1W2424, which is the module solution. So for the low voltage side, the PCB area is 25 millimeters squared for the 913, and then 120 millimeters squared for the MID 1W2424. The next biggest area is from the transformer, so that's 63 millimeters for the 18913, whereas for the MID 1W2424, it's fully integrated. And then if you look at the total area XY dimension on the PCB, the discrete solution actually is slightly smaller at 120 millimeters squared, whereas the module is 150 millimeters squared. But the biggest savings for the module is actually if you look at the Z dimension. So if you look at the max height with an external transformer, especially a bobbin transformer, typically that height is 9 millimeters or more. And then the MID1W2424 with its ultra compact profile, we're able to achieve a height of 2.65 millimeters. So really the biggest advantage of the modules is basically in the total height requirements from integrating the transformer. So if you're trying to put these power supplies on the backside of the silicon carbide MOSFET, or you have really tight height constraints, then the MID1W2424 power module might be a very good option to take a look at. Now, just to summarize everything that we just mentioned earlier, so on the left-hand side, we have the 18913, which is our gate driver power supply in an LLC resonant topology. And then on the right-hand side, we're comparing it to a competitor primary side regulated flyback topology. So with the 18913, we're able to achieve a very high switching frequency, all the way up to 10 megahertz, compared to 400 kilohertz or less with a PSR flyback. This results in a smaller transformer at the higher switching frequency. So we're looking at a 13 microhenry transformer in 11 by 6 millimeter package compared to a 30 microhenry transformer that's in a larger 10 by 10 millimeter package. And then one of the issues we have with flybacks is that as you increase the isolation requirements, you have to increase the size of the transformer. And typically that results in even more leakage inductance. And so for an LLC resonant topology, that leakage inductance is actually used as part of the resonant sink, whereas in a PSR flyback, as you increase that isolation rating, it induces voltage spikes and extra losses that come from the design of the transformer itself. For the LLCs, it's very easy to design up to 5 kV isolation. So as these systems are going from 400 volts up to 800 volts, 5 kV reinforced isolation is becoming more important, and that's what's really driving this isolation voltage spec. And then for PSR flybacks, anything really beyond 2.5 kV becomes really difficult to implement due to the higher isolation capacitance or even the higher leakage inductance that causes the extra voltage spikes and extra losses. If we look at the isolation capacitance, the LLC topology can achieve as low as 6 picofarad, and I've seen some of the designs we've done which are only 1 or 2 picofarads of isolation capacitance, whereas for a competitor PSR flyback, that isolation capacitance is 13 picofarad up to 25 picofarad, and I've seen some flybacks that go all the way up to 40 picofarads of isolation capacitance. If you look at the EMI performance, the LLC is a soft switching topology, so we do get much better EMI performance. And then if you look at the PSR flyback, it is a hard switching topology, so you will see quite a bit of overshoot on the switch node especially. If we look at it from a total solution size perspective again, the package size for the LLC is smaller, so 2 by 2.5 millimeters versus 4 by 4 for a PSR flyback. The total solution size is 109 millimeters squared versus 180 millimeters squared. And then we are also talking about less BOM components, so 21 components versus 26. So there's a lot of advantages that we see with these LLC topologies when you compare it to some of the legacy flyback applications that have typically been used for these gate driver power supplies. So if we look at isolated gate drivers, they are a key part of power converters by activating the switch, which drives the power conversion. These gate drivers take control signals from the primary side or low voltage side, and then it turns on or turns off the power switch on the secondary side. So in this case, this power switch could be an IGBT or silicon carbide MOSFET. And so it turns on and off this secondary side switch by either sourcing or sinking current to the gate of these power switches. And this is what really helps provide an isolation barrier between both the high voltage as well as the low voltage side. So as we can see, the gate drivers do need a power source on the secondary side, which is illustrated by the VDD on this diagram. So isolated power supplies are required for these gate driver circuits. So here, circled in red, we have our isolated power supply. It takes the input voltage from the primary side, and it generates an isolated output voltage on the secondary side. So an isolation barrier does have to be present between both the primary and secondary sides inside the power supplies, and typically that's provided by the transformer. In the renewable energy industry, we're actually seeing some interesting trends that put more requirements on the transformer design of these isolated power supplies. First, the battery voltage as well as the DC bus voltage is gradually transitioning from 200 volts up to 400 or 800 volts. And then in order to really facilitate higher power density traction drives and to boost up overall efficiency, uh, people are starting to use silicon carbide more and more often. And so when you see the shift from silicon IGBTs to silicon carbide MOSFETs for these converter designs to really take advantage of the high speed and low loss features of the silicon carbide device. So the higher switching DVDT operation of the silicon carbide actually drives a lot more current across the isolation barrier compared to IGBTs. And this noisy current can potentially disturb the normal operation of controllers and sensitive circuits on the low voltage side. And thus, we really need to minimize the isolation capacitance on the transformer as much as possible. And so the example we're showing here at the bottom, assuming each transformer has 20 picofarads of capacitance between the primary and secondary side, this is a pretty typical value, especially when you look at an off-the-shelf transformer. And when you see a silicon MOSFET that has a switching slew rate of 100 volts per nanosecond, this causes a common mode current across the isolation boundary that can be 1 amp, and that can be very dangerous to the MCUs on the board, your gate driver ICs, and even your gate driver power supplies themselves. So how can we deal with this new requirement for the transformer? So if we look at the interwinding capacitance, it can kind of be compared to a parallel capacitor as illustrated on the left side here. Since the insulation material and the area of the coil offer less design freedom, the best way to really reduce this capacitance is actually by separating the two windings. And this means increasing the thickness of the insulation layer. So if we look at the equation on the top right here, the capacitance is actually inversely proportional to the distance between the two winding coils. And thus, we really need to increase the distance to reduce the capacitance. And by increasing the distance, it can also increase the isolation distance, which increases the isolation voltage rating that you get from the transformer design. There is a cost to increasing this isolation distance between the windings. So when we increase the insulation thickness, this reduces the interwinding capacitor, but it also worsens the magnetic coupling between the two sets of windings. And this actually causes an increase in leakage inductance. And so there has to be a way when designing these sorts of power supplies to deal with this unavoidably large leakage inductor. And here on the bottom right side here, we have this leakage inductance modeled by this LLK. So one of the most frequently used topologies that we've mentioned throughout this presentation for these gate driver power supplies is a flyback converters. Flybacks typically behave like a buck boost converter, but the inductor is split to enable isolation between the input and outputs. And in these converters, efficiency is very closely linked to how tightly the primary and secondary inductors are coupled. So the increased leakage inductance loosens this coupling, so the amount of energy which is transferred across the inductor will decrease, and this causes a large loss in efficiency and also forces these power supply designers to select larger and more expensive components to accommodate these voltage spikes that are created by the leakage inductance resonance. And for this reason, flybacks aren't really the most ideal solution for these newer high power designs. And so just to illustrate a little bit more on how flybacks operate, when the switch turns on, the current will flow through the switch as well as the leakage inductance. When the switch is turned off, some power will store and the magnetizing inductance will be transferred to the secondary and hence to the output. The energy that's stored in the leakage inductance has to find a way to flow somewhere, and that causes resonance between the leakage inductance and output capacitance of the switch. And so that's what can result in these high voltage spikes across the switch. The switch node voltage spikes will increase the switching device rating, and this also complicates snubber design, generates losses and noises, and really limits the max operating frequency. So the larger the leakage, the worse the performance of the flyback. And that's really based on, the isolation rating that you're trying to design for. New technological developments recently have led to the adoption of LLC converters as the most efficient topology for isolated gate driver power supplies. So in the last few years, before products like the MPQ 18913 came out, a lot of this did have to be implemented discreetly. But now we do have these LLC converters that have the control logic as well as the FETs all integrated in one device. So these converters are based on a resonant LLC tank, which has a magnetizing inductor for the energy transfer, as well as additional capacitor and inductor whose purpose is really to make the tank resonate at a certain frequency. And the converter uses this resonance to ensure a highly efficient power conversion. And the main benefit of these LLC converters is that the leakage inductance created by the transformer can be used as the resonant inductor in the tank. And this really eliminates the issue of efficiency loss or voltage spikes associated with the flyback topology. And this is why really LLCs are the best choice for powering isolated gate drivers. And another good thing about these LLCs is that it is a soft switching topology, so we're able to achieve zero voltage switching. And this is the reason why high switching frequencies are achievable with an LLC topology. Here we have the switch node waveform of the LLC on the left-hand side, and then a competitor flyback. You can see that for the LLC, there is no overshoot on the switch node. That's this blue square wave here. And then if you look at the switch waveform of a flyback on the right-hand side, you can see that when the switch node hits, that there is quite a bit of overshoot as well as ringing on the switch node from the flyback topology. Here we can take a look at the input waveform of both the LLC as well as the flyback. So on the left-hand side, again, we have the LLC topology. You can see that there's not really any sort of overshoot for this on the input. Whereas on the right-hand side, we have the hard switching and a flyback. And you can see that at the peak, there is a little bit of overshoot. And that switch noise can actually couple back into the input rail, which you can see here. Yeah, so that's an in-depth dive on a comparison of an LLC versus a flyback. Now I'll talk a little bit more about some of the isolated gate drivers or gate drivers in the MPS portfolio. So just now I covered the MPQ 18913, the MID 1W2424, and there's actually one more, which is the MID 3W or MID 6W 2424, which I'll be covering as well a little bit later, which is a slightly higher power version of these power supplies. So first I'll take a look at this MP 18811, which is a single channel isolated gate driver. So the MP 18811, this has a MP 18811, which is non-automotive, and then we have MPQ 18811, which is the automotive grade device as well. So with the SOIC 8 narrow body, we're achieving a 3 kV RMS isolation voltage. And then in the SOIC 8 wide body, we're able to achieve 5 kV RMS between the input to output for isolation rating. The combo transient unity of this device is greater than 100 kilovolts per microsecond. We do have an output drive supply with different UVL options from 5 volts up to 15 volts, and the output drive supply can go up to about 30 volts. This is a very basic single channel isolated gate driver that's pin-to-pin compatible with a lot of the competitor products out there. So some of the competitors that we're pin-to-pin to include ST Micro, Infineon, as well as TI. For the non-automotive grade device, the source and sink current is 4 amp and 4 amp. For the automotive grade device, The source and sink peak current are slightly higher, so 6 amp source and 10 amp sink for the MPQ 1811. The propagation delay of this device is 50 nanoseconds typical. And for this 1811, we do have a active Miller clamp, but we do have a separate option that offers split output as well. And this is made really for operating junction temperature range from -40°C to 150°C as well. The next products we have a dual channel version of the MP1811. So this is the 18831, 51, and 71. So the MP18831 is a dual input half bridge that does offer dead time control. We have the MP18851, which is dual independent drivers. And then if you have a PWM input application, we do have the MP18871 as well. We have we have a number of different packages available depending on the isolation rating that's needed. So we have narrow body SOIC 16, which achieves 3 kV isolation. We have wide body SOIC 16, which can achieve a 5 kV isolation. We have an LGA 13 in a 5x5 millimeter package that achieves 2.5 kV isolation. And then we also have a version of this product which has 2 of the pins removed on the output. So you have a 3.3 millimeter creepage between the 2 outputs. For the non-automotive grade device, it's 4 amp source and 4 amp sink. And then for the automotive grade device, we have 4 amp source and 8 amp sink. The propagation delay for this device is 50 nanoseconds typical and 20 nanoseconds for the automotive grade device. And again, this gate driver can operate from -40 to 150°C Celsius for the operating junction temperature. And typically, this is also one of the products that is pin-to-pin compatible with several of the competitors out there. So if you're using dual channel gate drivers from TI, Silicon Labs, ADI, this dual channel gate driver is pin-to-pin compatible in several different packages. And typically we see these used for different applications such as solar inverters, any sort of DC to AC inverter, server power supplies, and half and full bridge converters. So next, I'll go back to some of the power supply options that we've talked about earlier as well. So this is another isolated power supply with the integrated transformer. So this is the MIE1W0505. So the reason why this is MIE instead of MID is that this is actually the second generation of these isolated 5-volt power supplies. The 1W means up to about 1 watt of power. So if you look at the input voltage range of this MIE1W0505, we have a 3 volt to 5.5 volt input voltage range. We have 2 different output voltage options, so either 5 volts or 3.3 volts. So with 5 volt to 5 volt or 5 to 3.3 volts, we can achieve greater than 200 milliamps of power, which is how we get the 1 watt power rating. And then if you go from a non-isolated 3.3 to an isolated 3.3, our max output current is about 50 milliamps and reduces the power rating to about 165 milliwatts. We do have excellent load and line regulation performance. We do have a host of different protection features such as short circuit protection, overcurrent protection, as well as over temperature protection. One thing I want to highlight here is that we do have 3 different package options available. So we have 5 kV RMS. This is a SOIC 16 wide body package. It's a fairly standard industry-wide package. It's 10.3 by 10.3 millimeters with a height of about 2.65 millimeters. So this can achieve the 5 kV isolation. We do have an SOIC 8 wide body that achieves 3 kV isolation. Then we also have the world's smallest isolated 5 volt to 5 volt power module right now, which is in this LGA 4x5 millimeter package. And this achieves a 2.5 kV isolation rating. So this LGA package is actually really great to place anywhere on your board for any sort of auxiliary power supply that does require 5 volts. It could be a digital isolator, it could be an isolated amplifier. But if you look at this package size, 4x5 by 1.18 millimeters, it's pretty crazy to see how small this module is with the integrated transformer as well. All these products have very low emissions for EMI, and we are able to meet CISPR 32 Class B requirements. And typically, as I mentioned earlier, we see this being used for BMS, digital isolator bias supplies, and even isolated amplifier supplies. So if you look at the evolution of power modules in the semiconductor industry, they really started out with these pretty traditional SiP packages. So the SiP packages typically have been, 20 millimeters by 6 by 10. It's a fairly large brick. And then with our last generation modules, we started creating this SYC16 wide body that was 5 times smaller than the SiP module. And then with this generation, we made it even 10 times smaller than the SYC16 wide body in a 4 by 5 millimeter LGA. So if you compare the LGA to this traditional SiP, that's only 2% of the size of a traditional SiP module. So we've really been able to achieve a great amount of power density, creating these tiny, very versatile 4 by 5 millimeter isolated power modules. We also have a higher power module. This is the MID3W or MID6W2424. So as I mentioned earlier, the MID3W is a 3-watt power supply and the MID6W is a 6-watt power supply. The last 4 digits does determine the turns ratio of the product. So if you look at the MID6W2424, MID3W2424, the turns ratio is 1 to 1. The 1524 products have a 1 to 1.6 turns ratio. So if you have a 15 volt input, it will give you a 24 volt output. And then we also have a 1 to 2 turns ratio available, which is the MID3W1224. So with a 12 volt input, we'll give you a 24 volt output. And then you can see in this block diagram, if you have a 24 volt output, you can do a plus 20 minus 4. You could do a plus 15 minus 8. And with a dial drop, you could even do something like plus 15 minus 3 or plus 18 minus 3 volts, depending on which vendor you're using for the silicon carbide power MOSFET. We do have very strong magnetic field immunity. Again, we have a host of different protection features such as short circuit protection, overcurrent protection, as well as over temperature protection. This is available in an LGA 10 by 10 millimeter package. The height of this MID6W is actually right around 4.8 millimeters typical. And then we have an operating temperature range of -40°C to 105°C. And again, this type of product is used for silicon carbide and IGBT gate driver power supplies, industrial automation, PLC input-output modules, and then grid protection relays. And any place you really need that plus or minus plus 20, a differential of 24 volts, so plus 20 minus 4, plus 15 minus 3. And here we show the efficiency for this MID 3W and 6W2424. So on the right-hand side here, you can see even up to 100 milliamps of power, we're achieving about 87% efficiency. So it is a very high efficiency solution for these gate driver power supplies. And then on the left-hand side, we show the output regulation at full load from 10% of the power to 100% of the power. And so that's pretty good as well with the 24, 21.6, or 26 volt input. The last product that we want to show off for these renewable energy applications is our digital isolator roadmap. So we do have both automotive as well as industrial grade products available. Our digital isolators are the MP279XX family. So the MP27, the way that we name our digital isolators is that the last 2 digits represents the number of forward and reverse channels. So this MP27933 is 3 forward and 3 reverse channels. The MP27931 is 3 forward and 1 reverse channel. And that kind of goes for all the 2-channel products, the 4-channel products, as well as the 6-channel products. So this is the MP279XX 4-channel and 6-channel digital isolator. Our digital isolators have a wide input voltage range from 2.5 to 5.5 volts. We can go up to 150 megabits per second for the data rate. We do have ultra-low power supply current as well as high electromagnetic immunity. You can see that we do have a number of 4-channel and 6-channel devices available. So the 4-channel devices are 4 forward, 0 reverse, 3 forward, 1 reverse, and then 2 forward and 2 reverse as well. And then for the 6-channel products, we have 6 forward, 0 reverse, 4 forward, 2 reverse, 3 forward, 3 reverse, and then we also have a 5 forward and 1 reverse channel configuration as well. And all of our 4-channel and 6-channel digital isolators are available in an SOIC 16 wide body package. And again, these digital isolators are pin-to-pin compatible to some of the competitors out there, including TI, Silicon Labs, as well as Maxim. And then we also have our family of 2-channel digital isolators. So again, the same great 2.5 to 5.5 volt input voltage range, up to 150 megabit per second data rates. We have 2 different packages available. So an SOIC 8 wide body, which can achieve 5 kV RMS isolation, as well as a 3 kV RMS isolation for the SOIC 8 narrow body. We do have selectable channel direction, so 1 forward, 1 reverse, or 2 forward and 0 reverse. And then we also have both default high as well as default low versions of this device. You can see in this typical block diagram, we do have the MID 1W0505 power supply, and now we even have the MIE 1W0505, which is that tiny 4x5 millimeter isolated 5-volt power supply. And again, this is pin-to-pin compatible with several different products from TI as well as ADI. So if you're looking for a pin-to-pin solution or a second source digital isolator solution, we do have that available. So that concludes the webinar for today. Thank you for taking the time to really learn about some of the isolated power solutions that MPS is offering for industrial, renewable energy, and EV ecosystems. And we hope that you're able to learn how to make the conversion from a flyback to an LLC power supply. And I hope that you tune in and come join additional webinars from MPS in the future. Thanks a lot.
Thank you, George. Now, if anyone has any questions, please use the QA button located at the bottom of your Zoom meeting interface, and we will answer them live. One of our most asked questions is if the session is being recorded. It is being recorded, and it will be sent out to all registrants and posted on our website within the next couple of days. And it looks like, George, we do have one question that just came in. Do you think that the digital isolator can also replace the octo coupler? I don't know if I'm saying that right, but I don't know if you can see it in the chat.
Yeah, so we have seen a lot of replacement using digital isolators for optocouplers. I think one of the big advantages of digital isolators is that in one IC you can get 2 channels or 4 to 6 channels of isolation, whereas for an optocoupler, for each channel of isolation that you're looking for, you do require to have one IC for that. Some of the other advantages are that optocouplers are based off of opto isolation, so you have an LED flashing on and off. And so typically, in terms of from a reliability standpoint, that's not as reliable as either magnetic coupling or capacitive coupling for some of these digital isolators. So, if your question is, can they replace an optocoupler? The answer is yes. But typically for digital isolator, you do need to have an isolated power supply as well. Whereas for an optocoupler, the power supply is kind of provided by the LED. But I think in total, from a reliability perspective as well as solution size perspective, digital isolators typically are a more preferred option as long as you need to isolate more than 2 channels.
Great, thank you. And we have another question. Will the recording link be shared to us? Yes, it will. Again, we will send it out to all registrants, and then we will also post it on our website. It will be posted by the end of this week. We just need a couple days to get it up and running. So the answer is yes. And then we have a couple other questions. Where are the main drivers for efficiency losses coming from with this LLC resonant topology for the MPQ 18913?
Yeah, so that's a good question. So if you look at the efficiency curve that we mentioned earlier, this is a fairly highly efficient topology. The main drivers for the efficiency losses are really coming from the transformer winding and the core loss. So depending on the sort of transformer that you design, whether it's a planar transformer or a bobbin transformer, the transformer design is what's really driving a lot of the efficiency losses for this LLC topology.
Great, thank you. Another question. Thank you for the presentation. Are these products and other chips of yours for sale, and can one use them for personal projects?
Yeah, all the products that I have shown to you today are on the MPS website, and so you can go ahead and go onto the MPS website, and you can either purchase it from MPS online, or you can also inquire about getting some of the samples online as well.
Great, thank you. Another question, where can we get the transformers that work with your LLC topology?
Yeah, that's a good question. So for the transformers for these LLC topologies, typically we can use any off-the-shelf transformer. The main thing that you want to look for these transformers is making sure that the turns ratio fits the input and output voltage ratio that you're looking for. So for IGBTs, typically I see plus 15 minus 8 volts. And then for the silicon carbide MOSFETs, I typically see plus 18 minus 3, or even plus 20 and minus 4 volts.
Great, thank you. Another question, do you have an LLC that can take 400 VDC and output 10 to 30 volt?
So today we don't have an LLC topology that can do that sort of conversion, but we are working on a flyback that can take 400 volts DC. The output's 10 to 30 volts. That product will probably be sampling early next year, but we have a flyback controller with an integrated silicon carbide MOSFET that can do the 10 to 30 volt output, probably in the 20 to 50 watt range.
Great, thank you. Another question, what type of capacitors are recommended across isolation regulator input and output, and why?
I don't think there's any sort of special capacitor that's required for these isolated power supplies. Typically, we are using ceramic capacitors, and then it's just, we'll use 50 volt ceramic caps for the input, and then on the secondary and output side, that's lower. We typically use 25 volt caps. So I don't think there's any special types of caps that are required. But for automotive applications, we do recommend automotive grade caps. And then for industrial applications, there might be a few more options as well.
Great, thank you. Another question, what sort of isolation technology is used for MPS isolated products?
Yeah, so that's a good question. So for the digital isolators as well as the isolated gate drivers from MPS, we use capacitive isolation technology.
Great, thank you. And then we have a couple more questions. How quickly will you be able to provide samples?
Yeah, so all the products that I showed today on the slides are sampling, whether it's the isolated gate drivers or the isolated power modules, as well as the digital isolators. Yeah, so everything can be found online at nps.com if you need more information, such as data sheets. And then we have samples and evaluation boards of all these products right now.
Thank you. And last question, do you have evaluation boards available now?
Yes, for all of our products that I showed today, we do have evaluation boards available as well.
And looks like we have one more that's came in. Do you think that flyback solution remains better than LLC topology in case of multi-channel outputs needs?
Yeah, so I think when you look at a flyback, typically we still recommend using flybacks if your application requires 10 watts or more. I think the multi-channel, as long as it's 8 watts or less or 6 watts or less, the LLC is still a topology that you can design a multi-output transformer. So for some of the designs that we've worked with, we've worked with some transformer vendors for really optimizing a 2 to 3 output transformer to be used with the LLC. So for example, in a traction inverter application, if you don't, for redundancy purposes, typically you have one power supply for each high side FET. And then for the low side FETs, you could use one LLC supply to bias all three low side supplies. So for an inverter, that's typically three phase. So that means you have 6 silicon carbide MOSFETs. The high side, you have individual LLC power supplies. And on the low side, you can use the multi-winding transformer to bias all three.
Thank you. And if anyone else has any other questions, I'll hold here for a few seconds, allow you to type. Looks like I'm not seeing any other questions. Thank you again for joining us today. We look forward to having you at our future sessions, and have a good day. Thank you.